So, um, just keep an eye on the website, just in case something with Monday, if we have class or not. I don't know what they're going to do. I don't know what's going to happen. So just keep an eye on that. Because we don't know what's happening with the tropical storm or hurricane or whatever it is. And otherwise, stay safe this weekend. Okay, so we're going to continue talking about solutions. And we talked about last time that a solution is, of course, made up of a homogeneous mixture of a solute, which is our component that changes state. In this example, salt, sodium chloride, and our solvent, which in this case would be water. And in a lot of the cases, we'll be looking at water, though that's not always true in all types of chemistry, but a lot of chemistry we'll be talking about, we'll be describing ionic compounds in water. So we want to be able to describe how much of each component is in our solution. Because, of course, it's not going to be the same with every sample. So we need a way to quantitatively get that across. So one way we do that is by describing something as concentrated or not. So, of course, solutions are often described as dilute or concentrated. And the more concentrated, that means the more solute you have versus solvent. That makes sense. So dilute solutions have a small amount of solute when you compare that to solvent, versus a concentrated solution has more. Where that distinction is between dilute and concentrated isn't quite clear, so this isn't the best way to explain a solution. And it's still not useful just to say I have a concentrated solution of sodium chloride, or make a concentrated solution of sodium chloride. Typically, we consider a concentrated solution being just to that point where it's not saturated. And a saturated solution is one where we have so much of our solute that it no longer dissolves. All of our solvent molecules are interacting with all of our solute molecules, and we no longer have any left over to dissolve anymore. But still, this isn't very good quantitatively. This is useful, but not very good quantitatively. So a more precise method to quantify the amount of solvent in the given amount of solution. And you can do that based on using a number to show the concentration. And occasionally this is described as the amount of solvent, but for the most part we're going to do this based on the amount of solutes. So based on this question, clearly 1.1 gram in 1,000 grams of water is going to be fairly dilute. It's not very much salt compared with the amount of water that we have. And remember, heterogeneous mixture means we'd have two separate components. We don't have two separate components. You can't tell the difference between the salt and the water. So the next thing we're going to talk about is the most common way to quantify our concentration. So the most common way that we're going to use to quantify our solution is going to be molarity, especially when we're talking about an aqueous solution where a solvent is water. Remember, aqueous means water. There are other methods that we'll talk about when we get to them, but this is our most common, and we're going to be focusing on that a lot. So, what is molarity? Molarity is just, the definition is the moles of solute per 1 liter of solution. Now that's 1 liter solution, not 1 liter of solvent. That's important, because depending on how much solute you have, that can affect your value. So this is 1 liter of solution. And this is always moles per liter. That's also important to remember, that your molarity is in the units of moles per liter. So what this tells us is the moles of solute per liter of solution. So if we have a molarity number, we have this. And that gives us a relationship, which we're going to get to. So if you know the moles of solute, or even the mass of solute, because of course we can convert that to grams, then we can convert grams to moles, then we can determine our molarity. And if we have a certain molarity solution of a certain compound, then that's going to have the same properties for any other molarity of that same solution. So this way we can quantitatively know what we have. So you must know this equation, know what molarity means, and know what units molarity is in, moles per liter. So what we typically do in the lab, and you'll be doing this when you take lab. If you're a chemistry major, you're in lab now. If you're not, you're going to be taking lab probably next semester. But what we'll typically do is use something called a volumetric glass, put a little bit of solvent, and add our amount of solute. Usually you start dissolving it a little bit. Once you add all of your solute, then you're going to add your solvent all the way to the fill line. And usually you're dissolving it as you do that. Once it's completely dissolved, you completely add it to the fill line. Because again, it's not liters of solvent, it's liters of solution total. So depending on how much of your solute you have, that can affect your volume. So that's also important to remember. And then that gives you, in this case, a 1 molar solution, because we're taking 1 mole of sodium chloride and dissolving it in a liter of water. So that's how we typically make it in the lab. So if you're given an amount, you can figure out your molarity. So in this case, we're finding the molarity of a solution. We know how much of our solute we have. Our solute is KBr. And we're told how many liters of solution we have. Now, if this is given in milliliters, we must convert it to liters, because our molarity is always moles per liter. So if you are given a certain molarity of a solution, then the units are always automatically moles per liter. So you have to convert this to liters. You have to know that unit, because oftentimes the units won't be given because it's understood the units are moles per liter. So we're given the mass of our solute, KBr. We're given the volume of our total solution. And we're given our molarity, which is M. We're looking for molarity. So first off, this is always moles per liter, but we're given mass. So we need to convert our solute mass to moles, which we can do easily. We've been doing that all semester. Once we do that, then we can convert our molarity, because our liter solution is already given. So to convert to moles KBr, we need to know our molar mass, of course. So if you don't have your molar mass, that's your first step. So our molar mass of KBr once you look in the periodic table, it's going to be 119.00 grams per mole of KBr. So now we have our relationship to convert to our moles of KBr. So we want our grams at the bottom. and our mole of KBr at the top. Of course, that should be 3 significant figures, so I'm just going to underline them, because I don't want to round just yet. I don't want my numbers to be off a little bit. So that's our moles of KBr that we added. So now we can figure out our molarity because we know our liters of solution. So we can divide our moles of KBr. And again, if this isn't in liters, we need to make that conversion. So when we do that, we find that our molarity is 0.122. And oftentimes, we'll use the M, but the uppercase M to represent molarity. So when you see the uppercase M, that's often how your molarity will be shown, as 0.122 molarity. So you should automatically know that that means moles per liter. And what that tells me is that I have 0.122 moles of KBr for every liter of solution. That's my relationship that my molarity tells me. So even if I only use, let's say, 25 milliliters of the solution, I can figure out how much solute is going into my reaction. And we're going to get to that in the next coming slides, how this is useful. So looking at this one's pretty straightforward. We have 125 moles of NaCl. Now this might be a little off because this is telling us how many milliliters of water. So this is our assumption here, is that we're adding such a little amount of sodium chloride that it's not affecting the volume. And in reality, we'd really want to know our total liters of water plus how much our solute is affecting the volume. The big thing here, though, you have to convert 1,000 milliliters to liters. This is always moles per liter. And that's how molarity is known. So you won't often see the units. You just know as soon as you see that big M, that means moles of solute per liter solution. So let's look at this one. Why do I have this one? Oh, so in this case, the milliliters, or our solution, is given to us in milliliters. So again, for this one, we're going to have to do some converting. We can't just take 3.4 grams of our solute and divide it by 200 milliliters. That's not our definition for molarity. So we're given our mass of our solute. Again, in this case, solute is NH3. And we're given our volume of solution, but our volume is in milliliters. So we have to convert. So not only do we have to convert our mass of our solute to moles, but we also have to convert our solution to liters. Once we do that conversion, then we can figure out our molarity. And of course, we're going to need the fact that NH3 has a molar mass of 17.03 grams, and you should still know your conversion from milliliters to liters. I like to use 1,000 milliliters equals 1 liter, but you can use this, it means the same thing. So if we're looking at that conversion, we first want our moles of our solute, but we're given our mass. So this is the same thing we did in the example previously. And if you're still having trouble calculating your molar mass, please come see me, because we're going to be using that in almost the rest of the class. So we have 0.3652 moles of NH3, and we need to figure out our volume of our solution in liters. We have our volume of our solution in milliliters right now. Once we have our volume and our moles in the correct units, Now we can figure out our molarity. And you can show the units as moles per liter, or you can show it as the big M. They mean the same thing. And oftentimes you'll see it both ways. So now that we know how to calculate molarity, why do we care? Yes? Oh, I'm sorry. I jumped to the wrong one. That's clearly not 200 either. So we have 1 molar solution. So now that we know how to do this, molarity is important because one of the reasons why we might make a solution of a reactant is because we're using a very small amount of reactant, so this allows us to deliver it well. So we might make a big solution, and we might only use a small amount of that solution. So we need to know how much solute we're actually getting into the reaction. Because water is just a solvent, and typically it won't be participating in the reaction. And for most of the reactions we'll be talking about, water can participate, but in these reactions they won't be. So we want to know how much of our reactant we're actually getting in the reaction. So we need to be able to use molarity in calculations. So molarity is just another relationship. What our molarity tells us is how many moles of solute per liters of solution. So for example, let's say we have a concentrated solution of sugar, and it's a 2 molar solution. So what that tells us is, for 1 liter of that solution, we have 2 moles of sugar. So we could calculate how many grams of sugar we have for 1 liter of solution, assuming, of course, you know the molar mass of sugar. So what that tells us is that we have a relationship and we have a conversion. For 1 liter of solution equals 2 moles of sugar, and we can use that as a conversion factor, just like we did for density. Now, remember, this is a very specific conversion factor. This conversion factor only works if your molarity of your solution is 2. If my molarity of my solution is 3, that would be 3 moles per liter. If I'm talking about a different solution, I need to know the molarity. So this is a specific, I can't always say a sugar solution has this conversion factor. I can always say there's 1,000 milliliters in a liter. I can't always say that this is my conversion for a solution of sugar. I need to know my molarity. So what that means is, if I, let's say, have a 2 molar solution of sugar, and I take 50 milliliters of it, I can figure out how much sugar I took out. Because I have this relationship, that for every 1 liter, I have a certain amount of sugar. So that's how we're going to use it. So let's say we have 2 liters, that means we have 4 moles of sugar. If we only have half a liter, then that means we have only 1 mole of sugar. So we have that relationship. So we can use that. And we're going to use that in, eventually we're going to work our way to use that into reactions. So we're going to start slow. So let's say we have a 0.125 molar sodium hydroxide solution. And we want to know how many liters that we would need of this solution to have 0.255 moles of sodium hydroxide. So we're given everything we need to figure this out. We know our concentration, and we know how much moles we want. So we can figure out how much volume we need. So looking at this example, our molarity is given to us. Our moles that we need are given to us. And what we're looking for is the volume that would contain this much moles. So first off, our relationship. The relationship that we need, because we already have moles, we already have liters. Our relationship that we need is given to us, and it's given to us by our molarity. Our relationship is the fact that in this solution, particular solution that we have, only the solution, but in this solution, we have 0.125 moles of sodium hydroxide for every liter of sodium hydroxide solution. So we have that conversion factor. So to convert moles of sodium hydroxide to liters, we need that relationship from our molarity. And that tells us that we have 0.125 moles of sodium hydroxide, not 0.125 liters of solution. Remember, our definition of molarity is moles of solute, our solute is sodium hydroxide, per liter solution. So do not interconvert these numbers. This 0.125 is tied to moles of solute. So this tells us that we have 0.125 moles of solute for 1 liter solution. I want to know how many liters of this solution I need for 0.255 moles. I should already know from this I'm going to need more than 1 liter of solution, because I'm asking for more moles than what's in 1 liter of solution. I want 0.250, but I only have 0.125 per mole. So you already have some information about the solution. I don't know how much solution I have. I just know how much solute is in how much volume of solution. So I already know some information. So I might have 5 liters of this 0.125 molar solution that I am then taking out a certain amount of. So this is how our relationship is going to work. So as long as you know what molarity tells you, you can use it as a conversion. So I am converting, what I read. My moles. I know I want this much moles. So I want to know how many liters of this solution I need. So my conversion factor is coming from my molarity. I'm going to have my 0.125 moles of sodium hydroxide at the bottom, and my liter of solution at the top. Again, do not interconvert those numbers. That 0.125 is tied to the amount of moles of solute I have for every liter of solution. So when I do this conversion, my moles of NaOH cancel out, and that tells me I need 2.04 liters of my solution to have the amount of moles I want. Now remember, this is my sodium hydroxide solution, and that's that specific solution. This wouldn't work for any other sodium hydroxide solution if it's a different concentration. This only works for this concentration. So my conversion factor is my molarity. And this makes sense, again, because for every liter, I only have 0.125 moles of sodium hydroxide. So it makes sense that I need more than 1 liter to have this much sodium hydroxide. Here's another example. In this case, I want to know I have 1.75 liters of a 1.50 molar solution of calcium chloride. I want to know how much calcium chloride do I have. I can do that. I'm told how much the volume I have, and I'm told my concentration. My concentration is that I have 1.50 moles of calcium chloride for every liter of solution. That's what my molarity tells me. As soon as you see molarity, write your relationship. So I know how much volume I have, and I know my concentration so I can calculate my mass. My conceptual plan, though, is that first I have to calculate my moles, because my molarity is a relationship between my moles of calcium chloride and my liter solution. So I first have to calculate my moles, and then I can calculate the mass, because I know my molar mass. I can find that from the periodic table. So my relationship to convert my liters of my calcium chloride solution to the moles of calcium chloride I have in that solution is my molarity. That I have a 1.5 molar solution. Sorry about that. So I have a 1.5 molar solution, so I have 1.5 moles of calcium chloride for every liter solution. And I also know I have 1.75 liters of solution. That means I have more solution than my molarity. I expect to have a slightly more moles. So I already have some concepts that I can figure out with this. My other relationship is, of course, to convert my moles of calcium chloride to mass. I need my molar mass from the periodic table. Again, if you have trouble calculating molar mass, please come see me, because we're going to be using that throughout the rest of this class, and I won't always be going through how to calculate it. So for this solution, I am taking the volume. So be really careful to read these. I have a bunch of numbers that are thrown at me. 1.75 liters, 1.50 molar solution. Make sure that you are not interconverting the numbers that are given. Don't lose your units. Make sure you're writing down your units. My volume is 1.75 liters of solution. My molarity is my relationship to moles of solute. That's just my concentration. So keep that in mind. Don't start with your 1.5 mole solution. You're not converting that. That is your conversion. That is your concentration. So my volume is 1.75 liters of solution. And of course it's a calcium chloride solution, because that's what we have. And I'm using my relationship of my concentration to convert that to moles. Because I know I have 1.75 liters of this solution, and I know for every liter I have 1.50 moles of solute calcium chloride. So my 1 liter solution of calcium chloride is going to go at the bottom. And my mole, 1.50, is going to go at the top. Again, if you're following your units, you will not have a problem. So now I have this in moles. But I want to know my mass, so I have to take this further to convert this to mass. And I have to use the molar mass on the periodic table. So my 1 mole of calcium chloride goes at the bottom, because I know for every 1 mole of calcium chloride, I have 110.98 grams calcium chloride. That's what my molar mass tells me. So this will give me my answer in mass. So that's 291 grams calcium chloride. Again, this is my relationship, my molarity. As soon as you see that molarity, rewrite it as moles of solute, whatever your solute is, per liters of solution, because that's your relationship. Well, here's another example. What if I wanted to prepare 250 milliliters of a 0.150 molar calcium chloride solution? How would I do that? So the thing is, what are we asking? So what I'm really asking is, how much calcium chloride do I need to weigh out? to dissolve to get a total of 250 milliliters of solution and have a molarity, a concentration of 0.150 moles of calcium chloride per liter. So I already know my volume. I'm really just trying to figure out the mass of calcium chloride I'm going to need to dissolve to get a total volume of 250 milliliters. So I'm doing basically the same thing as in the last example. It's just the question is asked differently. Because here I'm trying to prepare this. I only want 250 milliliters, and I want to make sure I have 150 moles of calcium chloride per liter. But the math is going to be pretty much the same. The big difference, though, is my volume is given to me in milliliters, and remember, my relationship is moles of calcium chloride per liter solution. So I will have to convert my volume to liters to be able to do this. So first off, I'm given my volume, my total volume of my solution that I want. I'm also given the concentration that I want, and I want to find the mass that I'm then going to dilute to 250 milliliters with my solvent. So my plan is to, well, first off, my relationships. My relationship from my molarity, which is 0.150 molarity calcium chloride solution, that's what I'm trying to make, means that for every liter of solution, I want there to be 0.150 moles of calcium chloride. That's what I want. So that's my relationship. That's what my molarity tells me. And of course, I know my relationship between milliliters and liters. I'm going to need that as well. And because our molarity is in moles per liter, I need my concentration. My relationship between moles and my mass of calcium chloride. So again, that's from the periodic table. So the first thing, I want to know how much mass of calcium chloride that I need. So I'm starting with my 250.0 milliliters. That's what I want of calcium chloride. It's my volume. And I know I want a certain concentration of that solution. So I'm using that relationship. But remember that relationship is in liters, so I first have to convert this to liters. And SOLN is just me shorthand writing solution, because I'm not going to write out solution every time. So if you see SOLN, that's just solution. Now that we have this in liters, now we can use our relationship of our molarity. So what we know is for every liter of solution, so that'll be at the bottom, I have 0.150 moles of calcium chloride. So this will give me how many moles of calcium chloride I have to dilute with 250. Well, dilute to 250 milliliters. Of course, we can't really measure out moles. We measure out mass. So we have to figure this out in mass. In the lab, we're not measuring out moles. We're going to measure out our mass. So we have a balance, but we don't have any way to measure out moles. So that's where our relationship from our periodic table comes in, where 1 mole of calcium chloride equals 110.98 grams. Moles of calcium chloride cancel out, and that comes out to 4.16 grams calcium chloride. That's not quite the end of the question. The question is, how would you prepare it? I would prepare it by measuring out 4.16 grams of calcium chloride and then adding my solvent until I have a total volume of 250 milliliters. That's how I would actually prepare it. I know my total volume is 250 milliliters, it's told to me. So all I needed to find was how much solute I had to have to get to that amount. So that's the actual full answer to how you would prepare it. So when we're preparing a solution, we start with knowing the amount of the total solution and our concentration of solutions. And then we can calculate the mass of the solute needed. We just did an example of that. And we use our concentration as a conversion factor. There's other ways concentration is sometimes shown. For example, you might see a solution that's a percent by mass, meaning you have 5% by mass, which is 5 grams of solute, equals 100 grams of solution, that's just 5%. You might see by volume, that's by volume. We're not really going to be talking about that so much right now. We're going to be sticking with molarity for most of this chapter. And molarity is, like I said, the most common moles per liter, but you might also get a mass percent or a volume percent or volume by volume. So those mean slightly different things, and we'll touch on that later on. Now, then we're going to take that grams of solute and dissolve it in enough solvent to equate the volume that we are trying to get to. And we just did that in the example before. The next thing we're going to talk about is dilutions. So often, I might store something as a concentrated stock solution. Maybe it's salt, water, whatever. But then I might want to take some of that concentrated solution and add more salt to make it a more dilute solution. And there's multiple reasons why I might do that in the lab. So I might take a stock solution and add more solvent to then dilute it and make it at a lower concentration. One thing to note, the amount of solute does not change, because I didn't do anything with the amount of solute per liter. But I'm adding more solvent, so the concentration changes. So we can use a conversion for that. So, I don't know, I accidentally put the slide in the wrong place. So this question, we had a sample, it had 25 milligrams of solute, then we added 1,000 milliliters or 100 milliliters of solvent. Actually, it doesn't matter, I could have added 10,000 milliliters of solvent. Still going to have 25 milligrams of solute. I didn't do anything with my solute. I didn't add any more. I didn't take any out. I just added more solute. Now my molarity is going to change because my moles per liter are going to change. The concentration is going to change. But my total amount isn't going to change. If I make Kool-Aid and I take a sugar packet of Kool-Aid and I add a cup of water, I have 1 sugar packet. If I add another cup of water, how much sugar packet do I have? 1. I didn't change the amount of sugar packet. So that's our dilutions. And based on the fact that we're not changing our amount of solute, we can use that as a factor to dilute solutions. So our moles of solute in solution 1 is going to equal to our moles of solute in solution 2. But our volume is going to be different. So we can use this equation, molarity of 1 times volume of 1 is going to equal to molarity of 2 times volume of 2. Where does that come from? That comes from the fact that my moles is going to be the same on both sides. Because remember, Molarity is moles per liter. So even though my volume changes, my moles don't change. So you can know this as M1V1 equals M2V2. If you know your molarity and how much volume you have of one, you can figure out how to make a solution of another concentration. So we just need to know 3 of these things, and then we can calculate the 4th. So again, the basis of this is the fact that our moles do not change. We have the same amount of moles in each solution. We just have a different amount of moles per volume, but the same amount of moles. If you taste the difference between that Kool-Aid solution that you only added 1 cup and the one that you added 2 cups, it's going to taste different because the one that you added 2 cups has more water per sugar packet. But the same amount of sugar was added. The difference is how dilute you made it. So this is all we're doing here. If we know this, we can make a dilution. And again, the reason why is often we will store stock solutions, but we don't need that concentrated of solution, so we will then dilute it. So let's look at an example. So we had, what is the concentration of solution prepared by diluting 45 milliliters of an 8.25 molar HNO3 to 135.0 milliliters. So what that told me is, I took 45 milliliters of solution 1 at this molarity. That's our concentration. I have 8.25 moles of HNO3 for every liter of HNO3. I took less than a liter. I took 45 milliliters. 1,000 milliliters is equal to a liter. So I took less than that. And then I took that and I added enough solvent to change my volume to 135 milliliters. My question is, what is now my concentration? I now have the same amount of moles, but I have a different amount of volume. So I need to calculate that. So the hardest thing for these for most students is assigning M1V1, M2V2. Because if you get that mixed up, then you're going to get the answer wrong. So make sure you're paying a lot of attention to what the question is saying. What this question is saying is, I took 45 milliliters of a solution that had the concentration 8.25 moles. So that means that M1 is 8.25 moles and V1 is 45. I took that solution, I had it in, I had it labeled, I took 45 milliliters of it. Then I put it in whatever, a volumetric flask, and I added more solvent to where now my total volume is 135 milliliters. That's V2. I'm trying to figure out the concentration of that now, because I don't know what the concentration is. So that's going to be my M2. That's my concentration. Remember, your molarity is your concentration. So you really have to pay attention to what the question is telling you to make sure that you set this up correctly. The math isn't hard, but you have to make sure that you are reading the example. So we're given M1 and V1, and we're given V2, so we're trying to figure out M2. And of course, our equation is always M1 V1 equals M2 V2. So we're given our V1. V1 is the volume that we took out, which is 45.0 milliliters. That 45.0 milliliters had a concentration of 8.25 moles per liter. So that is my M1. Now, we didn't change my solute either. In both cases, my solute is HNO3. I don't really need to know that to answer that question. But my solute's never changing. I'm also not really told what my solution is. I'm assuming it's water. But we don't really know. And that's not necessary to answer this question. So then I'm told that I took that 45 milliliters that had 8.25 moles per every liter. And I diluted it to 135 milliliters. So that's my total volume after I diluted it. So that's my V2. I'm looking for is M2. I do not know it. Now you could convert these to liters, but it's not going to be really necessary because V1 and V2 are both in milliliters. So you're going to get the same answer if you converted them both to liters. So it's not necessary for this example. And I'll show you why when we plug it in. So again, our equation is M1V1 equals M2V2. And we are looking for M2. I like to rearrange my equation before I plug in my numbers, but that's up to you. You can rearrange it after. And if you have problems rearranging equations, please come see me. I can work with you with that. That's an algebra course, and this is just applying algebra. So, we're looking for M2. I can divide both sides by my V2. My V2 cancels out. So my equation is M2 is equal to M1V1 over V2. Again, if you need help rearranging equations, please come see me. I don't really have any time in this class to teach the basic algebra skills. So now I can just plug that in, but again, the key is assigning these values correctly. So it wouldn't be correct to say V1 is 135 and M1 is 8.25 because once I dilute it to 135 milliliters, I no longer have that same concentration. Now this is why I don't necessarily need to convert my volumes to liters, because notice milliliters cancel out. So as long as my volume for V1 and V2 are in the same units, they will cancel out because that's just a ratio. So if I converted them both to liters, it would be the same ratio because I'd be doing the same conversion for both. So you can if you want to, it's not necessary. I'm not doing anything with my molarity units, so it's staying the same. And it should, because my final answer I'm looking for is molarity. That's going to be moles per liter. So my milliliters cancel out. So when I do this actual calculation, what I will get is a solution that has a concentration of 2.75 molarity, or 2.75 moles of HNO3 per liter. Which you can show as moles per liter, or you can show with the M. They're both accepted. This makes sense because I diluted. So my final answer should be less concentrated because I took 45 milliliters of something and I added enough solvent to make it 135. I didn't change the solute, so I made it less concentrated, so this molarity should be smaller. So you can always go and check your work. Also, if I calculated M1 times V1 and then I calculated M2 times V2, my moles would be the same. So you can check that as well. If I calculated the moles I have in 45 milliliters of V1 and the moles I have in 135 milliliters of V2, they should equal the same moles. So that's another check you can do. If they don't, then you did something wrong. But of course, we can use some understanding about this. So I'm going to do one more before we end class today. Just because, again, the math isn't really hard here, but typically a common mistake for these examples is assigning M1 and M2, M1, M2, V1, and V2 wrong. So let's go through another example. So this one asks, how would I prepare a 200 milliliter amount of a 0.25 molar NaCl solution from a 2 molar NaCl solution. So what does this mean? So this means that I have a 2 molar sodium fluoride solution that's in my lab. I want to take a certain amount of that solution and then dilute it to 200 milliliters, and I want the final concentration to be 0.25 molar NaCl. So I am given, in this case, M1, and I am given V2 and M2. That's really important. So I'm looking for the amount V1 that I need to take out to then dilute. So in this case, I need to find V1. So I'm given M1. M1 is my bigger concentrated. It's my more concentrated solution. And then I'm told that I want to make a total volume, so that's V2 of 200.0 milliliters. And I want that final concentration, M2, to be 0.25 molar, or 0.25 moles of sodium chloride per liter. So what I'm looking for in this case is V1. I don't really have any relationships here, I'm just solving for this equation, but the key is assigning M1 and V1 correctly. Otherwise, you're going to get the wrong answer. So really talk out what the question is asking you to do. So again, I know M1 V1 equals M2 V2. So I'm going to solve for, in this case, my V1. So my V1 is going to be equal to M2 V2 divided by M1, which I have. And if I want my final volume to be in milliliters, I don't have to worry about doing any conversions. So I'm trying to make a 200 milliliter volume of my final solution, and I want that to be 0.25 molar. And I'm starting with a 2 molar solution. My moles cancel, my molarity, moles per liter, is on both the top and the bottom, so that cancels out. So that'll be left with milliliters. So when I do this conversion, I find that my V1, I'm sorry, my calculation is not a conversion, is, let's see where I have this written down. Ah, here it is. 25 milliliters. And of course, 2 significant figures, because this is only in 2 significant figures. It depends what it's asking. My answer doesn't have to be in liters. My molarity is in moles per liter. I can measure out any value. If I wanted to calculate how many moles, I would have to convert this to liters.
So when you ask for volume, it doesn't matter if you say it's kiloliters or liters?
It depends what I ask. If I say give me the volume in liters, give it to me in liters.
This one it wouldn't matter.
It doesn't matter, I wasn't specific. So since my other volume was in milliliters, that's fine. Now if I wanted to calculate my moles in 25 milliliters, I would have to convert it to liters, because my relationship is moles per liter.
So would it be wrong for me to put 2.5 instead of negative 2 liters? Would that be wrong?
If you put it in liters?
Yeah.
No, that's not wrong. You can convert it to liters. It just depends on what I'm asking for.
Okay.
So in the lab, I can take 25 milliliters and dilute it to a total of 200 milliliters. If I were using my molarity relationship to figure out what that's going to show, I need to convert it to liters because that's what I want. But I think that is milliliters. We never did that.
I just want to make sure my answer how
But it depends what I'm asking. If all my if I ask for milliliters or if all my answer choices are in milliliters, it's gonna be a 1.
So if you put the volume and just whatever the value is, and then.
I mean, if I'm not specific, that's the easiest.
Alright.
Oh, I'm gonna push it back.
Thank you. I was just wondering.
Oh no, your homework will never be due until. I'm gonna double check.
I'm sorry.
Have a great weekend.
You too. Y'all be safe. Pay attention to the website.